Welcome to Derechtronic, where we experiment, learn, and build with electronics. As a follow-up to my most recent video, where we constructed an inverting operational amplifier, this time around, we will be constructing a non-inverting operational amplifier instead. But before we go into that, let us first compare the inverting op-amp from the non-inverting op-amp through their input and output waveforms. Let's start off with the inverting op-amp. Its input-output waveform is as follows. See here on the left. Now, the input waveform is the one in black, the smaller one. The output waveform is the one in blue, the taller one. As we can see right here, if we will try to describe the relationship between its input and output waveform, we can say that the waveforms are out of phase. They are not starting and ending at the same time. And their phase relationship is 180 degrees. Why 180 degrees? Now, as we can see here, that when the input is in its positive half cycle, the output is in its negative half cycle. And when the input is in its negative half cycle, the output is in its positive half cycle. This is what is known as output inversion. The output is the inverse of the input. If the input is positive, the output is negative. If the input is negative, the output is positive. And the 180 degrees here is indicated through the separation. We make use of 360 degrees as reference. 360 degrees would be one complete cycle of a waveform, of a sine wave. That's one positive and one negative alternation of a sine wave. And we can see here that the actual separation of the two waveforms here, the input and the output, is half of a cycle. So half of 360 would be 180 degrees. Hence, phase relationship for the inverting op-amp waveforms is 180 degrees. Now, for the non-inverting op-amp, which we will be constructing today, their input-output waveforms will look as follows, the one here on the right. So, let's now try to describe the relationship between the input and output waveforms here. The input waveform is the one in black, the smaller one. The output waveform is the one in blue, the taller one. Now, for the non-inverting op-amp, their input and output waveforms relationship are as follows. We can say that the input and output waveforms are in phase, unlike in the inverting op-amp. Why in phase? Because both the input and output waveform will start and end at the same time. If you make use of one cycle, or for each cycle, one cycle as a reference. Okay? If you take a look at the cycle for each, it's starting and ending at the same time. And what else? We can also say for the non-inverting op-amp that the phase relationship is 0 degrees because there's no actual separation between the two waveforms. So once we built our circuit later on and open the companion software for the COM3 lab board that we will be using, we should expect the oscilloscope waveforms to look something like this for our circuit today. Schematic diagram of our non-inverting operational amplifier circuit is shown here. As you can see from this diagram, we will still be using a 741 integrated circuit. The pin out, I'm also illustrating here on the right side here. Similar to the inverting op-amp, we will still use 5 pins from the integrated circuit, from the IC. That will be pin 2, pin 3, pin 4, pin 7, and pin 6. Now, the output, which is pin 6, will be connected to the feedback resistor, RF. We will use this time around a 10 kilo ohm resistor for the feedback resistor here. Now, that feedback resistor is connected in series to our input resistor, which will also have the same value, 10 kilo ohms. And our input resistor will be connected to ground. Now, pin 2, which is the inverting input of the op-amp, the 741 IC, will be connected to the junction between the feedback resistor and the input resistor, as you can see right here. Now, the non-inverting input, pin number 3, will be connected to a capacitor, the negative terminal of the capacitor. The positive terminal of that capacitor will be connected to the positive terminal of our function generator. Now, pin 4 and pin 7 of our op-amp, which actually serves as, you can see right here, the positive voltage and the negative voltage supply of our op-amp, will be connected to negative 15 volts and positive 15 volts respectively. Now, similar to our inverting op-amp, we will set the function generator here to output a sine wave, the frequency and amplitude of which we can set to any value actually. Now, for this demo, we can actually set the sine wave to have the following frequency and amplitude value. Maybe we could set it to 2 kilohertz frequency and maybe 2 volts peak to peak amplitude. Now, just like the inverting op-amp, since this is also an amplifier circuit, we should expect that here at the output on pin 6, if I connect an oscilloscope here, we should expect that the waveform here at pin 6, when we connect the oscilloscope, would be an amplified version of the input waveform that we will see on from the function generator. It's amplified. Now, the factor of amplification, or the amplification factor, would depend on the gain of the circuit, of the non-inverting operational amplifier circuit. Now, the gain of the non-operational of the non-inverting operational amplifier circuit, same like the inverting op-amp, would depend on the values of the feedback resistor and the input resistor here. The formula is as follows. Gain is equal to 1 plus the ratio of the feedback resistor over the input resistor. See here. Now, the capacitor that you see here between the function generator and the non-inverting input, we call that capacitor a coupling capacitor. We saw something similar to this one in the inverting op-amp circuit. The only difference is that here, in the non-inverting op-amp, we connected the capacitor to pin number 3, which is the non-inverting input. In the inverting op-amp circuit, we connected the capacitor in series with our input resistor, and that branch was connected to the inverting input, non-inverting input, pin number 2, in the inverting op-amp circuit. It's connected to pin number 2. Now, question, what is the function of this capacitor here? The main function of this capacitor is to allow only AC signal to pass through. It will block any DC offset signal coming from the function generator, which normally happens from time to time, especially if the function generator is a little bit old already. Now, any DC offset that will pass through will have an undesirable effect on the output of the amplifier. So we need to block that DC offset signal and just allow AC signals to pass through. Let us now construct the non-inverting op-amp circuit discussed earlier. Again, just like in our previous videos, we will use the COM3 Lab protoboard for this purpose. The 741 IC I've already inserted on the board here. A closer look at that here. What I did here is that the notch, or the half moon notch on the circle that marks pin number 1 is actually here on this side, facing to the left. Now, if that is the case, just like as we learned in the previous video, okay, pin number 1 would be here, upper left, okay, 1, 2, 3, 4 for the first 4 pins. At the other side, pin 5 would be there on the bottom right, 1, 5, 6, 7, 8. It's here. Now, we'll do is this. Okay. Let us first connect the components connected around this 741 IC. Okay. Starting off with the resistors, the input resistor and the feedback resistor. Now, if you could remember from the schematic diagram earlier, okay, we will be using two 10 kilo ohm resistor as the feedback resistor and the input resistor respectively. Now, in this circuit, the circuit for this demo, we have the same value for the input and the feedback resistor. However, be careful because what if you're given different values for the resistors mentioned? So, kindly take note of this, okay? Based on the diagram shown earlier, the feedback resistor should be connected to pin 6 in series with the input resistor, and the other leg of the input resistor should be grounded. Now here, there's no problem. I can interchange it. However, if you're given different valued resistor, be careful with the connection. So I could use either one of this as feedback, either one of this as input. There's no problem. Let's connect it now. So the one I'm going to use for the feedback resistor, let's say this one, okay? I'm going to connect it to pin number 6, which is somewhere here. Connect it here, pin number 6. I'll connect the other leg somewhere here, like that. Okay. Then the input resistor, same value, 10 kilo ohms. By the way, how do I know it's 10 kilo ohms? Again, you just have to take a look at the colors on the body of the resistor, okay, as basis for that one. Okay, for the input resistor, I'll connect it in series with the feedback here. And the other leg would need to be connected to ground. So I'm going to connect it to a power rail at the top. Connect it to the blue power rail at the top. One of the blue power rail. Here at the top, here, maybe here, there. Like that. Okay. So if the blue power rail at the top here would be my ground, if the blue power rail at the top would be my ground, so the function generator, which serves as my input, the function generator is here on the left. You can see here, function generator. The negative of the function generator would have to be connected to the blue power rail. Let me do that now. So negative function generator, or the ground of function generator, connects to the blue power rail there. Okay, now, if you can remember from the schematic diagram, what you need to do is here, okay? Pin number 2, the inverting input, would have to be connected to the junction between those two resistors, the feedback and the input resistors. Let me do that now by using a jumper wire. Okay, let's do that now. Pin number 2 here to be connected to the junction between the two resistors. Let me do that here. There. As you see there. Between the two resistors. Connected. Okay. Now, on pin number 3 of the 741 IC, we need to connect a capacitor. So based on the schematic diagram earlier, we need to use a 10 microfarad capacitor, the one I have here, 10 microfarad capacitor. The negative, the shorter leg, will have to connect to pin number 3. The positive, the longer leg, will have to connect to the positive terminal of our power source, which is our function generator, AC power source. Let me do that now. So the negative, shorter leg will connect to pin 3, like here. And the positive, I'll connect it on the free pin on the other side of the gap of the separation here. Let me just do that properly first. Okay, there. There. I have it there. Closer look. Show you. Here. Okay. Pin 3. Connected to pin number 3. Pin number 3 here. Now, other leg on the free. Now, that leg, that leg, the positive terminal, okay? What I'll do, similar to what I did before, okay? I'm going to connect that leg to a power rail, okay? So what I'm going to do, using a jumper wire, another jumper wire, I'm going to connect one jumper wire here, and I'm going to connect to a power rail here down. I'm going to use the red power rail here. Why is that? Because if you could remember again, according to the schematic diagram, that capacitor would need to connect the positive terminal of that capacitor would need to connect to the positive terminal of the power source, which is our function generator. So the out pin here will have to be connected to the same line where this jumper wire is connected, which connects to the capacitor here, the positive terminal of the capacitor. Let me do that now. So out wire, out pin, positive, or I'm sorry, red side of the power rail. There. Function generator connected. Now, what's left here are the connections of the power pins or the power supply pins of our 741, okay? Which, according to the schematic diagram, will come from here. Positive 15 and negative 15 from here. So what I'll do right now, I'll connect positive 15. You can remember the diagram before. Positive 15 will connect to pin number 7. Do that now. Pin number 7. Here. Pin 7. There. Okay. And negative 15 volts will connect to pin number 4. Pin number 4. Pin number 4. Somewhere here. There. Okay. Pin number 4. Pin number 4. There. Pin number 4. Pin number 7. Closer look, maybe. There. See, this is positive, negative 15, pin number 4, and this is positive 15 connected to pin number 7. Pin number 7 here. Okay. And the ground terminal of the fixed supply, I have to ground that also. Connected to the common terminal, our common terminal, the ground connection for our function generator is here. The black here, which is the blue power rail at the top. So I'm going to connect the ground terminal of the power source to the same line where the function generator common is connected or ground is connected. I'll connect it here at the top. There. Ground. Now, this more or less completes the connection of our circuit. It's completed now. Now, what's left is the connection from the oscilloscope. Let's connect the oscilloscope already. Okay? Just like in the previous video, I'm going to use both channels, Y1 and Y2, the oscilloscope, okay? Y1 and Y2 here, and common. So I'm going to have connections on all three. Y1 will be used for the input, Y2 for the output, and of course the common connection or the ground connection. So what I'll do is this. For the input waveform, Y1, I will have one wire. Okay, this one's connected to the input. Where is our input? Our input is the function generator, the out terminal of the function generator, which is this one. It's the input. So I need to connect it on the same line where this function generator is connected. So you connect this one now to the red line here, or the red power rail at the bottom there. That's your input. Now for Y2, which I'll connect to the output, I'm referring to the output of our 741 IC. The output pin of the 741 IC is pin number 6. So I'm going to connect Y2, this one, to pin number 6. Same pin where that resistor, this feedback resistor, one leg, the left leg of this feedback resistor is connected. So you could actually see it here. See, pin number 6. Same connection where this resistor is, same line where this leg of this resistor is connected, that the feedback resistor. Okay. Now, and for the ground, common here, common pin of our oscilloscope, I'm going to connect it to the common connection where the ground of both the DC supply, the positive and 15-volt DC supply, and the function generator is connected here. These two black wires here. So I'm going to connect it here on the blue rail. Okay, on the blue rail, blue top on the top blue rail there. Now, this more or less completes the connection. So what is left to do here? I just need to switch on the board from here. Switch on the board from here. Set the function generator to output a sine wave with the frequency of 2 kilohertz and an amplitude of 2 volts peak to peak. And after that, I can switch on the power supply here, the fixed power supply here, so that I can power on the 741 IC. Here we have the companion software of our COM3 Lab proto board, where I have just set the function generator to output a sine wave with a 2 volts peak-to-peak amplitude and a frequency of 2 kilohertz. As you can see from here, lower left-hand side, sine wave, 2 kilohertz, 2 volts peak-to-peak. Let us now open the oscilloscope of the COM3 Lab software. From here, let me just put the display here on the right-hand side, a little bit bigger. There. Okay, now. So what we need to do here first, since I'm using both channels of the oscilloscope, I will have to put a check on Y2 first. Okay, I'll click preview and I'll run the oscilloscope now. Here. Okay, here's the output waveform. You can see it already. Now look at the waveforms. Okay, the one in black, the one you see here, is the input waveform. The one in blue, the one you see here, is the output waveform. Now, I'll put both of them on the screen. See what happens here. Now, notice something first. Let's take a look at this one first. The black one, or the input waveform, is actually directly above, or actually it's running through the zero line. Let me just make that clear. Let me just put first a trigger on Y1, and I'll just put it in one sweep, so this is clear. Okay, now. Okay, here's the input waveform again. It's directly above the zero line, or the origin of our oscilloscope. Okay, which means you could actually clearly see where is the positive and negative alternation of the sine wave here for the input signal of our circuit. However, for the output, if I show you the output now, let me just take out Y1 here. Okay, notice that the output is slightly above the origin or the zero line of the oscilloscope. What happened there? Okay, what happened here is that a few or a couple of maybe a certain value of a DC offset actually entered our 741 IC from here. If you remember my discussion on DC offset, the one being prevented by the coupling capacitor to enter our 741 IC earlier. Now, what happened here is that a certain value of DC offset entered through the 741. Okay, you might be wondering why did that happen. We already have a capacitor on the circuit, a 10 microfarad capacitor on the circuit. The possible reason there is this. Okay, it is possible that the value of the capacitor is not enough to prevent that DC offset coming from the function generator. So how do we fix this now? Okay, that display, so that this will look better. Okay. Now let me do something like this first. Okay, what I have right here is a 100 microfarad capacitor, electrolytic capacitor, which is actually 10 times the value of what we have on the circuit right now, which is a 10 microfarad capacitor. So what I will do is that I will replace the one we have on the board, the 10 microfarad capacitor, with this one, and see what effect it will have on our waveforms, the output waveform in particular. Okay, the position of the output waveform. Let's do that now. I have just replaced the 10 microfarad capacitor with the 100 microfarad capacitor. So the 10 microfarad capacitor is here now in my hands. So what I have on the board right now is our 100 microfarad capacitor connected the same way I connected this capacitor at first. Now, let us see what effect will that have in our circuit, and our waveform in particular, this one, the output waveform. I'll just put the trigger back to off first, okay? Then I'll run this one. Now, see the waveform now. I'll put it in Y1 again, trigger at Y1, and I'll put it in one sweep. See the output waveform now. This one is better. The output waveform now is running along the zero line of the oscilloscope. You can now see here clearly the positive alternation of this waveform and the negative alternation. Unlike the one earlier where it's slightly above, there's a DC offset if that happens. Okay. See here, right there. Here's the full waveform here. See here, right, guys? So see, you now see the effect of that DC offset. So it's possible that whenever you see a DC offset on the output waveform, highly possible that the value of the capacitor you use on the circuit is not enough to prevent the DC offset coming from the function generator. You might need to put a higher valued capacitor with a higher capacitance on the circuit, connected the same way. So you can see here. Now, using this waveform now, just put it clear here, bigger so that you can see bigger. Now, let us now try to verify the peak-to-peak values of these waveforms. Now, remember, we made the simple computation of the amplification of our circuit, the amplification factor of our amplifier circuit. We came up with the value of 2. And I mentioned earlier that, okay, our waveform should have more or less the same amplification, which means the input waveform here would be amplified by that much also based on the computation of the amplification factor. If our amplification factor is 2, theoretically, then I should have also have 2 here. How do we verify that? Let's check the peak-to-peak voltages of both. I'll start with the input waveform, peak-to-peak voltage of the input waveform. We get it first. Peak-to-peak value, okay? One of the vertical cursors here, the vertical cursor blue would be the one at the bottom here. And let's compute, okay? I can compute from here, right? Okay, Y1 red, the red vertical cursor there is at 1 volt. So by 1 volt minus Y1 blue, the blue cursor here, vertical cursor, negative 1.06. That will be 1 minus negative 1.06 will give you around 2.06 volts peak to peak, which is actually the setting of our function generator, the input, our amplitude on the function generator. 2 volts peak to peak, as you can see here. Now, let's take now the output waveform. Let me select the output waveform first, here. Output waveform. And I'll remove the input waveform. Let me take again the peak-to-peak value here, okay? One here at the top, one at the bottom. There. See that? There. There. Okay. Now, here's the peak-to-peak value. The output waveform. Let's just fix there. Okay. So what do we have here at the bottom? Okay, we have Y1 red, 1.94 volts mentioned here, and Y2 blue is at negative 2.13 volts. So I have 1.94 minus negative 2.13. So what you'll get there is around 4.07 volts. So we got 4.07 volts on the output waveform, peak to peak, and we have 2.06 volts on the input waveform, peak to peak. So more or less, the output waveform is about twice of that of the input waveform, which actually confirms our theoretical value, the theoretical value of our amplification factor, which is 2. Now, another thing, I forgot to mention this in our theoretical discussion. Now, the reason why the circuit that we just have constructed is known as a non-inverting operational amplifier. You can see here that there's no actual inversion of the output on the waveforms here. When the input waveform is in its positive half cycle, the output waveform is also on its positive half cycle. And when the input waveform is in its negative half cycle, the output waveform is the same. It's also on this negative half cycle. There's no actual inversion. Unlike in the inverting op-amp circuit, the output, is actually an inversion of the input. When the input is positive, the output is negative. And when the input is negative, the output is positive. In the inverting operational amplifier, here is not. Here is not. Okay? So you can see right here, no actual inversion. So it's a non-inverting operational amplifier. Another thing, phase relationship. You could also see it here. How? Okay? Notice there's no actual separation on the waveforms here, both input and output. Both of them are starting and ending at the same time. If you take one cycle, that's very clear here. So if there's no actual separation on the waveforms, the phase relationship for those two waveforms would be at 0 degrees. With that, I would like to end our discussion for today. And as always, I would like to encourage everybody to keep experimenting, keep learning, and I hope to see you next time here on Derek Tronic.